بسم الله الرحمن الرحيم. بنرحب فيكم في محاضرة جديدة عن الستوكاستيك أو الراندوم فاريبلز and stochastic processes. اليوم رح نتعرف على كونسبت جديد واللي هو the concept of a random variable. طبعا احنا سابقا تكلمنا عن probability theory، وفي معظم الأحيان كنا نعمل بعض التجارب اللي بتخص يعني بعض رمي قطعة نقود، رمي قطعة نرد، وناخذ النتائج. لكن احنا مش هذا يعني أهمية هذا الكورس مش في هذه الأمور. أهميته في دراستنا في الأرقام أو الفاليوز، الريل نمبر فاليوز اللي ممكن تتغير نتيجة إنه مثلا ممكن تكون سيجنال، فولتج سيجنال، أو بعض الأمور اللي بتخص شغلنا في الاتصالات أو في النتورك ثيوري اللي فيه بيكون فيها نوع من الراندومنس. فلذلك إحنا التجربة أو الراندوم بدنا نربطه مع الأرقام الحقيقية، وربط الراندومنس مع الأرقام الحقيقية بتكون من خلال الراندوم فاريبل. as a definition random variable is a number x of s assigned to every outcome S of an experiment. خلينا ناخذ مثال بسيط نعزز هذا الديفينيشن اللي احنا اخذناه. خلينا نحكي كالتالي. ناخذ المثال A في تجربة in the die experiment، في تجربة حجر النرد. we assign to the 6 outcomes Fi the number x of Fi equals to 10i. لاحظوا ان التجربة هون الاكسبيرمنت عندي Fi اللي هي مكان الاس، x of s x of Fi equals 10i. This means that x of F1 equals to 10 because it's 10 times 1. X of phase number 2 is equal to 20, and x of 6, the last one is f of 6, is equal to 60. So this is an experiment. So you have 6 different values of x. Each one of them is 10, 20, and 60. Notice that the probability of x of f1, which is equals to 10, is equal to 1/6. And the probability of x of f2 is also equals to 1/6. And the probability of x of f6 is also equals to 1/6. Okay, 1/6. So this is an example of, random assigned x assigned. So we assign a real number instead of the experiment. So you have 6 different values of x. X has the values. So x has the values 10, 20, 30, 40, 50, and 60. So we forget about the experiment itself and we take the numbers right now. And so you have a random number with discrete values, 10, 20, 30, 40, 50, and 60. And you deal with those real numbers. Let me take another example for the same experiment. So in the same experiment, we assign the number 1 to every even outcome. And the number 0 to every odd outcome. Thus, so x of f1 equals x of f3 equals x of f5, and all those are equal to 0, and x of f2 equals x of f4 equals x of f6 is equals to 1. Now, here you have x equals to 0 and 1, and probability of 0, of x equals 0, is equal to the probability of f1 plus the probability of f3 plus the probability of f5. This equals 1/6 plus 1/6 plus 1/6, and this is equal to 3/6, which is equal to 1/2. And probability of 1 is equal to the probability of f2 plus probability of f3 plus probability of f6, and this is equals 1/6 plus 1/6, 1/6, and this is 3/6. This equals, sorry, this is equals to also 1/2, which is reasonable here. Half of the events are mapped to 0, and the other half is mapped to the real number 1. Okay? In both experiments, or in both transformation from the experiment to the random variable, we have discrete values of x, not the continuous values of x. So random variables could be discrete, continuous, or mixed. Part of it discrete and part is continuous. Okay? If we want to just look at a continuous random variable as an example, continuous random variable, let's take the wheel of fortune. The wheel of fortune. We have a wheel. It starts from 12, 3, 6, and 9. And we have here an arrow. So the experiment here is you try to hit the arrow and see where it will settle down, at which number you will set, it will settle down, and you will take money, or you can pick whatever you want when you have a number here. So if this is the case, then our x here, if x is equal to s, then x is random variable such that x is greater than 0, less than 12. So our random variable x between 0 and 12, and it is continuous, means that every real number is equally likely, or all real numbers, let me put it this way, all real numbers are equally likely. Okay, so if we say what is the probability that x is between 0 and less than 3, we can say that, okay, it is 3 minus 0 divided by 12 minus 0, and it's equal to 3 over 12, and this is equals to 1/4. Okay? So here we have a continuous random variable between 0 and 12. Okay, let me just try to put things more in order, and we discuss the conditions for a function to be a random variable. Conditions for a function to be a random variable. Okay? Is it any function that in real life can be a random variable? What are the conditions for a function to be a random variable? First of all, it has to be a function, not to be a function not multivalued. When you say a function not multivalued, it means that we cannot have, you can have a function with the same value, like this. This is a function with two different x's, x1 and x2, which have the same y. But we cannot have something like this. One x has two y's, y1 and y2. This is multivalued, not function. This is function. It's a function. Okay? So this is a multivalued. You have the same x has two different y's. This is not supposed to be a function. This is a multivalued relation. So this is a multivalued relation, but this is a function. It's not one-to-one, but it is a function. So this is the first thing that we have to make sure that it's a function. It's not a multivalued relation. Okay. The second one, the set the set x less than or equal small x shall be an event for every real number x. Okay, just let me finish this sentence and we'll talk a little bit about this. The probability P of x less than or equal x is equal to the sum of probabilities of all the elementary events corresponding to x less than or equal small x. Of course, when you are dealing with real numbers, this has no problem. This is always satisfied. But imagine that if x, let's say, equals to red, green, blue, let's say, then what is the, let's say, what is this to have x less than or equal blue? So this is not a random variable. All the values here should be real numbers. The values of x should always be real numbers. Okay? So this one is not a random variable. Okay. Now, the third point, the probability that x equals minus infinity should equal to 0, and the probability that x equals infinity should equal to 0. This does not mean that we are not allowed to go to infinity. We can go from minus infinity to infinity, but the probability at infinity and at minus infinity should equal to 0. So those are the conditions for any function to be a random variable. Okay. Let's take a small example. If we have s equals to 1, 2, 3, and 4, and we have x of s equals to s cubed, then x is equal to 1, 8, 27, and 64. If we assume that we have probability of 1 equals 4 over 24, probability of 2 equals 3 over 24, probability of 3 equals 7 over 24, and probability of 4 equals 10 over 24. Notice that if you add those 4 together, then you have the probability of the sample space, which is the certain event. 4, 3, 7, 7, 14, plus 10, it's 24 over 24, which is equal to 1. Now, when you map x through s cubed, then you map also the probabilities to the corresponding values. So probability of x equals 1 is equal to the same as probability of s equals 1. So this is 4 over 24. Probability of x equals 8 is equal to 3 over 24. And probability of x equals 27 is equals to 7 over 24. And the last one, probability of x equals 64 is equals to 10 over 24. Okay? Okay. I will take one continuous example just to demonstrate a point that is very important here. Let me take the temperature somewhere. Let's take continuous random variable, and we have temperature T somewhere, which is supposed to be a random variable over the range minus 60 degrees Fahrenheit to plus 120 degrees Fahrenheit, and all the values are equiprobable. They are equiprobable means that all the values inside have exactly the same probability. Now the probability, so you have a probability over t from minus 60 degrees until 120 degrees. Now if I need to see what will happen if we have a probability, let's say between 70 until 95, let's say, or 90. So 70 until 90. What is the probability of x is greater than 70, less than or equal 90? So this is 90 minus 70 divided by 120 minus 60, so it's plus 60. So this one is minus 60. So 90 minus 70 is 20 divided by 180. So it's equal 1/9. Okay? So the probability is equal to 1/9. Let me now choose, so if we choose any dt here, where dt is very small, so the probability of dt, which is a value that is very small, is equal to dt divided by 120 minus 60, and this is equals to dt divided by 180. As dt approaches 0, very small value, then probability of dt is equal to 0. What does that mean? It means that the probability probability of discrete event on a continuous random variable is equal to 0. Which means that what is the probability of x equals, or T, sorry, temperature, T equals 90. 90 means that you are having some delta T that approaches 0, and this is a discrete event on a continuous random variable, and the probability is equal to 0. Okay? Now, to study the random variable more, we have to define some functions over the random variable. And the first function that we need to define over the random variable is the probability distribution function. And shortly, we call it the distribution function. So it's a function, and its definition is as follows. The distribution function of the random variable x is the function f sub x of x is equal to the probability that x is less than or small x. Okay, so this is a function of x defined for every x from minus infinity to infinity. Okay, so this is the definition of such a function. The subscript is the name of the random variable. So sub x, this is the name of the random variable, and x here is our independent variable that moves from minus infinity to infinity. Okay, we can also say that we have fx of x. We can say also we have fy of y. So this one should be capital for the random variable, and fz of z. We can also have some fx of some w, which is equal to the probability that x less than or equal this w. So w is a variable, x is the random variable. Okay? Okay. Let's take an example and see how can we demonstrate the distribution function. If we remember the S, which has the H and T in our experiment, where probability of H is equal P and probability of tails is equal Q, and P plus Q equals 1. So this is a biased coin. It's a biased coin. So it's not 1/2 and 1/2. One of them is P and the other one is Q. This is just to demonstrate an example only. So let's define the random variable as x of h equals to 1 and x of t is equal to 0. So we have x equals to 0 and 1. So you have only two values. Find find fx of x. Which is the distribution function. So the distribution function graphically, we have x as a random variable. We have the value of 0 and we have a value of 1. Now, if we go for x going from minus infinity to infinity, all the values below x has a probability of 0. So x, which is tails, has probability of this one. So probability of x of tails, which is equal to probability of 0, and this is equals q, and probability of x of h, which is equal probability of 1, this is equals p. So before 0, you have nothing, you know what I mean? So fx of x for equals 0 for x less than 0. Yeah? Because fx of x for x less than 0, this is equals probability of x less than 0. If it's not equal to 0, then you have 0 here. Once fx of x equals to q for x greater than or equals 0 less than 1. So you have q until 1. At 1, fx of x equals p plus q for x greater than or equal 1. So here you go up by p, so you have p plus q, and the answer here is 1. So you have this staircase function for the fx of x. Any value greater than 1, then you accumulate the probabilities, because this is an accumulation of probabilities. The probability of x, when we say that fx, let's say, of 5 as an example, this is equals the probability that x less than or equal 5. So this is, the 5 is here, so all the probabilities below 5, it's p plus q. So this is equals to p plus q, and this equals to 1. If we take the continuous case, and we have x or t belongs to the period between minus 60 degrees until 120 degrees Fahrenheit, then we can say that if this is ft of t, and this is our t, so at minus 60, it will start increasing. This one, it accumulates values until we reach 120, and then it goes like this, constant. Okay, so this is 1. And the slope here can be found, which is the The slope is, I think, 1 over 120 minus 60, it's 1 over 180. So this is the slope. 1 over 180. So the slope is 1 over 180. And if you go between those, 120 minus 1 is 120 divided times 1 over 180, then you end up with 1. Okay, so this is the slope of this curve. At 0, if you apply 0 here in this curve between this one and this one, so the accumulation will be at 0, it's 0 minus 60 divided by 180, and this is equals to 60 over 180, so it's 1/3. So this is 1/3. Okay. See that the distribution function, whether it is continuous or discrete, it starts from 0, it goes up, and then at infinity it should reach 1. Okay, so those are some of the properties of the distribution function. Okay, so properties of fx of x. Property number 1, fx at minus infinity is equal to 0. Second, fx at infinity should equal to 1. Third, so fx at minus infinity is 0, fx at infinity is equal to 1. So fx of x for any value is greater than or equal to 0, less than or equal 1. Okay. Number 4, fx of x1 is less than or equal to fx of x2 if x1 is less than x2, and this means that your non-decreasing function. What does that mean? It means that fx of x will never go down. It stays constant or increases, but it will never go something like this. It does not go down and goes up. It is always constant or increases. As x increases, fx of x either stays constant or increases. Okay, 5. Probability of x between x1 less than or equal x2 is equal to fx of x2 minus fx of x1. Prove it. Yeah, I will leave it as an exercise for you to prove it. Okay, and last one, 6, fx of x plus is equal fx of x. This means that the function fx of x is continuous from the right. Fx of x is continuous from the right. Now, properties 1, 2, 4, and 6. And 6 may be used okay to test if some function say gx of x is a valid distribution. Is a valid distribution function or not. Okay. So looking at the discrete case, we can represent the discrete case by the unit step function. So if x is discrete, then we can say that fx of x is equal to summation from I equals 1 up to n p of xi times the unit step of x minus xi. Okay? Where u of x is the unit step function. U of x is equal to 1 for x greater than or equal 0, 0 for x less than 0. So if we remember the case where we have the unit step for q, and then this is 1, this is 0, and this is p, and the end result is 1. So that was for the case of example 1, here fx of x. So we can represent fx of x here as probability of 0 is q times u of x plus p times u of x minus 1. So this is the representation of our example that we had before. Okay? Okay, there is a partner for this function. The partner is the density function. The density or the probability density function. Probability density function is the derivative of the distribution function. Fx of x is called the probability density function of the random variable x. So fx of x, we use a lowercase f instead of the uppercase f, so it's dfx of x by dx. Okay. Now, if we take the example here, which is the discrete case, and find, so you take this example here. Find fx of x for fx of x, which is equal to q u of x plus p u of x minus 1. We can say that fx of x is equal to q delta of x plus p delta of x minus 1. And graphically, this is two impulses, one at 0 with an amplitude of q, this is at x equals 0, and the other one is p at x equals 1. So this is q at 0, and this is p at x equals 1. So this is x, and this one here is fx of x. One impulse at 0 and one impulse at 1. Okay, so this is fx of x. If we take the continuous case that we had before with the temperature, so we got it's minus 60 degrees, this is 120 degrees, and this is the temperature at 1, and this is ft of t, the temperature in a certain area. If we need to find the derivative of this one, so the derivative of this one will be the slope, which is equal to 180. So between those two and 0 outside. So this is 0, and this one here is 1 over 180, and this is ft of t. So this amplitude is 1 over 180, okay? And so this is at minus 60 degrees, 120 degrees. Okay. Let's see the properties of the density function. Okay, so for the discrete case, we can say that fx of x are the derivative of the unit steps. So we end up with the, from I equals 1 up to n, p of xi times delta of x minus xi's. So you have impulses as we show in the discrete example. Now looking at the properties of fx of x, we can say that, first of all, that fx of x is always greater than or equal 0 for all x. And this is clear because the fx of x is the derivative of the distribution function, and the distribution function is a non-decreasing function. So its slope is always either 0 or positive. So the slope of the distribution is the density. And as long as the distribution is non-negative, then this is true. Second, the area under the curve for fx of x dx is always equals to 1. The area under the curve is equal to 1 because the area under the curve for this function is the probability of s, which is equal to 1. Third, I will leave this as an exercise for you. Fx of x. Now, this is the opposite of the derivative. The derivative of fx of x is the density function. So the derivative of the distribution is the density. But to find the distribution from the density, you have to integrate. So the integration from minus infinity to x, fx of z dx should equal this. Okay? And we use here the dummy variable because the upper limit here is the x that we are looking for. Okay, fourth property, the probability of x greater than x1 less than or equal x2 is equal to the integration from x1 up to x2 fx of x dx. Okay. Of course, properties 1, 2, properties 1 and 2 may be used to test if some function, let's say g x of x, is a valid density function or not. Okay, so those are the properties. Please try to prove it, and this one also prove it. I will leave those as an exercise for you to prove it. Okay, in the next lecture, we will study certain or specific random variables with their distribution functions. Okay, I will leave this for next lecture. Thank you very much, and I hope you will find this lecture very interesting. شكرا لكم، الله يعطيكم العافية.